Thank you very much for this nice introduction and for inviting me. I very much would have preferred to came in person to Lyon, but times are as they are. So my talk is about fraud, error, and I'm stress a bit more. I focus on fraudulent behavior in science. I start with some case studies, some examples of fraud in science, just to give you an impression. Then I will outline some methods of the diagnostics of fraud. I'll deal with systematic errors and the work of Humanities, and I conclude with why we need replications. Now, let's start with some case studies. And this was a very big scandal in the 90s in Germany. It has a large impact also on the German Science Foundation. It was a scandal in cancer research. And what did these people do? Friedel Hermann and Marion Brach. And they basically manipulated scientific illustrations, graphical presentations by manipulating. You can see here, this is from the report of the task force of RAP in 2000, and you can see these pictures are the same, and so, but you cannot see it on first glance. It was really, nobody became aware of this over a time span of more than a decade, and about 100 publications or even more were falsified by this team. So there was another big scandal, or there are many, but these are quite instructive, in physics. And this is Hendrik Schön falsifications of semiconductors. They were the co-authors who were not guilty on fraud, and they all thought they were on the way to the Nobel Prize, but all the data were faked. And what you can see, same thing, that these measurement figures from various publications. You can see here, these were different measures in different publications, and it was simply the same curve. Even the noise was very similar, and nobody became aware of this. However, it took by a whistleblower, there was information by a whistleblower, and it took about 2 to 3 years to detect the fraudulent behavior. So here, this is a case of very rapid self-correction of science. This is an old classical case in psychology. Cyril Bird is well known as in the 50s. He was the most prominent researcher in intelligence research, and he did this with twin studies, twins reared together, twins reared apart. And you can see here, if you look on these figures, usually nobody would suspect that there is some that there might be fake involved, but have a closer look on this. Now here are two correlations: a correlation for the identical twins reared together and twins reared apart, and there are 83 number of pairs, 21, and 11 years later, he enlarged his studies, and now he has 12 more twins reared together and 32 more reared apart. And what happens there? compare 1955 and 1966. And what did we get? The same correlation up to the third digit. But nobody became aware of this, and years and years passed, and then by several people who, there was a psychologist, Carmina, who outside person in this area of research, and he is a suspect, and then other documents, and later on in his autobiography or his papers, they found out that he completely behaved made this up. So this, but what I want to say is that we figure out often by inconsistencies in statistical figures. So, but usually reviewers miss it, and they are, of course, they are not responsible. You cannot, as a reviewer, always find out that there is fraud involved. Now, whistleblowers are very, very important, and we have to protect the whistleblowers. Duplication of figures is very common in science fraud. There's now software to detect duplications, and some journals employ this software. And there's data manipulation in numbers, and there are some statistical methods, and I want to show you some of these methods. Think of a little bet. For example, I ask, say, Jerome, let's bet on the first digit of the house number of Uljana, please. And hopefully, I think we both do not know the house number of Uljana. So the loser, say, a hypothetical bet on 100 euros. And I will win if the digit is in the range 1 to 4. And Jerome will win if the digit is in the range 5 to 9. Yeah. So it seems it's a good chance for Jerome and a worse chance for me, because 5 to 9, that's one figure more, but it is not. It's not a fair bet, because these numbers are not distributed evenly. The odds are 7 to 3 in favor of me, and this is because that house numbers, or first digits of house numbers, are distributed by Newcomb-Banford's law. Originally, it was Newcomb who detected this law, and Banford later on reinvented it. So here I have the first digits of house numbers we collected from Swiss telephone directory. And what you can see is that the digit 1 is much more overrepresented than digit 9, and it is quite exactly fits to the Banford distribution. This is a Banford distribution. It's a simple log distribution, and it's 30% for digit 1, 5%, 4.6 for 9. So 1 is about more than 6 times more frequent than number 1. And the idea I had is that we can use this method, this distribution, to check for scientific numbers. Before it was applied, the idea to use this Banford law for detecting fraud was by others, by Nigrini for business data, but I thought maybe we should try it for scientific data. So here's Nigrini's work on text data, and you can see these digits from real text data is Benford distributions, but here is a fraudulent text declaration, and this is deviates from the distribution. So, but you have to figure out whether the scientific data are really Benford distributed. Not all data are Benford distributed, but many data are Benford distributed. I'm sure if you draw a sample of, say, trees in Lyon, you measure the height of the trees, and the first digit of the height of the trees is surely Benford distribution. I bet for this. So I draw a sample of from articles in the American Journal of Sociology. We looked on all the regression coefficients, first digits, and the first digits of the regression coefficients are very in accordance with the Benford distribution. The same is true for the second digit. The second digit is more evenly distributed. And now checking for this, I can apply the method and I can ask, okay, what's about falsified data? And what I figured out, we constructed experimentally falsified data with probants. And what I figured out is that particularly there's a large deviation for the second digit. So my recommendation was when you do Benford tests, use the second digit distribution for this. Yeah, now a word of caution. Benford, there are hundreds of articles on UCOMP Benford distribution and applications in many areas. For tax fraud, accounting fraud, even states, statistics, interviewer fraud, election fraud, and so forth. And I used it for fraud and science. However, I won't deny that there are some weaknesses, and the thing is that there might be large errors to overlook fraudulent data, even if they are present. This is false negative, and there's also a possibility of errors that you are wrong with your suspect of fraud, so false positive. So what I see now is, honestly, Benford is at most a rough screening device, but it has some virtues, but you should know also the shortcomings of this method. Simonson employed different methods. He used simulation techniques, and I admire his work very much. From desktop research, he figured out many examples of fraud. And here I have a very nice spectacular example. This is, I call it Senna's hot tomato soup. Lawrence Senna published a paper in a reputed journal on his hypothesis, rising up to higher virtues, experiencing elevated physical height uplifts, pro-social actions. So if you are in a physically higher position, you are more pro-social. That's his hypothesis. It's surprising, surprising hypothesis. And how did he test it? He made an ingenious test. He placed subjects in a theater. So the first treatment group was in the orchestra, downstairs. Then there was a control group in the medium height audience, and a third group on stage in the high group. The dependent variable was to figure out pro-social behavior. Pro-social behavior was these probants had to fill. It was covered as a marketing study, and they had to give the stooge subjects, they had to give them a hot tomato soup. And the more they gave them, the less they were pro-social, yeah, because it was hot and uncomfortable to consume. So and then he could say in milligram how much tomato soup gave the subject to the stooge person. And this was a measure of pro-sociality. Okay, let's have a look on the results. And just here on study 3, what we find, it's exactly confirms the hypothesis. So there is 39 milligram in the high position, and 85 in the low position. Yeah. So the higher, the more pro-social you want to save the subject, so to say, from the hot soup, and the medium value is in the control group. And also for the other experiments, all the same pattern. Yeah. All in accordance with the hypothesis. So, but nobody is aware of what, if you have a first glance or even a second glance on this table, you wouldn't see that the standard deviation, this is by Simonson, he marked it. You see, this is a standard deviation of 25, 24.58, 25. So it's very, very similar. Yeah, and he became aware of these standard deviations. And his method is now, how likely is it that this standard deviation has such a small variability? And now we can do this by statistical simulation method. And what did he figure out? This is Sanner's data. It's extremely unlikely, and if you put all his experiments together, that we have such narrow standard deviations. It's a chance of 15 in 100,000. So this is really, shows that there might be fraud involved. However, he applied further tests. He tests the variability with other studies by other psychologists. And you see here that this is Sanner studies variability is much lower than in the other studies. So this is, so to say, a control group design. You also prefer more tests. And then what happens? The study was retracted. And he did this all from, even without knowing the data, the original data. And by the way, there are crazy implications of this study. What are the implications? Say, are Swiss people more pro-social than people in the Netherlands? Yeah. Or if the people lift up to a mountaintop, do they donate more than people staying in the valley? That are implications of the hypothesis. So I mean, a journal editor of a reputed journal, yeah, they like these spectacular, these surprising results. The same with Stapel, that they produce these surprising results, and journalists like to publish it, and they are uncritical. I mean, as an editor, I would ask, is this really true, and would do some checks on this. And what happened? Okay, retracted. Yeah, and Simonson discovered many more by this method, by these methods. A lot of fraudulent cases. Okay, let's go to systematic errors in with significance testing. There are many disciplines, most empirical disciplines use it in biomedicine and the natural sciences and social sciences. And we know the test strategy. We know that we test on a null hypothesis, and that we have a predetermined type 1 error, maybe 5%. And then there's a better error that we wrongly accept the null hypothesis. And we have a statistic, then say it's a simple test with a normal distributed data. The critical value is 1.96 for alpha 0.05. This is Lyman-Pearson test statistics. And what happens in practice? Here is a study, and this is called the Caliper test. So if there are true tests, we would expect that the values just before the critical threshold of 1.96 would have the same height as the frequency of tests thereafter. However, there's a large gap. What does it mean? That people either fake a bit the data, that they nudge it to jump over the threshold, or by publication bias. Both is possible. So these are simple tests. I think it's a nice thing, the Caliper test, that at least something happens which is not expected by applying regular statistics. And now there was this, many of you know this paper, a very, very nice, interesting paper based on basically on the Bayesian reasoning. And I want to give you the argument in a nutshell. Just the key argument in one graph is, okay, we assume we have conventional statistical tests, alpha 5%, power 80%, beta error of 20%. And now imagine, by this scheme, it's easy to understand what Ioannidis' argument. We start with, say, there are 10,000 hypotheses, 10,000, maybe in genetic research, there are 10,000 genes or so, and which might be susceptible for one trait. Now, from 10,000 hypotheses, we have a priori probability that 4% may have true effects are related to the trait in the genetic example. So 400 are true, 9,600 are false. So with an 80% power, we identify 320 as positive, significant, and 480, because of 5% false positive, 480 as false positive. So we, in all, we have 800 positive. So 800 significant results. These are published in the journals, the 800 results, and 480s are wrong. So we have a 60% error rate. We read these journal articles, and more than half, 60% are false. Simply, even if there is no fraud, even with a normal science process. So what can we do against this? And the antidote is replications. And now let's do a replication, and with these figures. And same parameters, we have 800 significant results, 320 true, 480 false positive. Replication with new data. So the 320 with a power of 80% leads to 256, which are significant and true. and the 480 wrong findings, and we will figure out by 5% alpha error, they leave 24 significant and false positive. So together, this is 280. There are 280 significant results after one replication, and 24 are wrong. So we have now an error rate of 8.6%. So replication reduces the error rate of 60% before to 8.6% afterwards. There's an example by Munising, and he gave this illustrative example from genetics. There was a survey of 600 positive associations between gene variants and common diseases. And then they made 166 reported associations were replicated 3 or more times. And in the end, only 6 were replicated consistently. What we read in newspapers very often is that this or that gene is responsible because these are the announcement, and this is what is left after several replications. So replications, 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 and I end with this with this list of recommendations. I'm sure there are more measures, and Felipe Romero also told about this. This is not new to you. So we should stimulate awareness on statistics and methods, and even in courses for students and researchers. Conducting replications, that should become a standard and obligatory part of academic education. For example, why not there now in psychology, also sometimes in sociology and economics, there are cumulative doctoral dissertations. Why not devote one part of the dissertation to replication work? And also journals should demand that authors give access to well-documented data files. There were several presentations before. There are a lot of problems with this, but in principle, this is an important issue. And also journals should consider to include a replication section, and funding agencies are asked to spend resources on replications. And maybe a more provocative suggestion: why not have an institution, a research institution, state-funded, who is responsible for, say, drawing a sample of research papers, and then to have a look on the papers and to replicate the papers. Same thing as evidence-based medicine institutions or agencies for nutrition, for food control. Why not have such an institution in science? So thank you very much.